Good morning, everyone. Welcome back to the eighth lecture of the workshop of PWF Sudan, Expanding Horizons in Physics in Sudan, the second edition, about the density functional theory methods and applications. Today's lecture will be given by Dr. Christian Carbogno, a group leader of the theory of heat and charge transport at interfaces at the Fritz Haber Institute of Max Planck Society. He is a lecturer at the African School on Electron Construction Methods and Applications. His group of the theory of heat and charge transport at interfaces research group focuses on the electronic and atomistic mechanisms that underlay the energy and charge transport in complex materials and the interfaces. Also, the development of more accurate and powerful first principle methodologies. It's an honor to have you, Dr. Christian. So you can share now your slides and let's start.
Yeah. Thank you very much for this kind introduction.
Yeah.
Let me share again. And I think you're seeing my slides now, hopefully, if everything
Yes.
worked out. So just organizational. Shall I plan for a break in the middle? Is that what we usually do? Or
Yes, exactly. We can have a 5 minutes break at 9:55 and then another break uh,
yeah,
if you want. Also it's an interactive lecture. Would
yeah.
you like to have the questions during or at the end of the lecture?
I would very much like to have them during. So if there's anything that you don't understand or that is unclear, please stop me immediately so
Okay.
that we can try to go into the topic a little bit more in detail because I don't know the attendees that well and I'm not sure what exact background is. So maybe sometimes stuff is too easy and too basic and then stop me and say, please go faster. And
Okay.
sometimes maybe I'm skipping some steps and you need more insights, then feel free to tell me, please keep it slow. Can you explain again? I would love to have that feedback. I think that is important for all of us for making this lecture a success.
Okay, perfect. So if there is a question, participant will raise the hand and they will also write in the chat. I will read the question for you.
Yeah.
Okay.
So just in case, if because with full screen and so on, I'm not sure if I always see the chat. If you notice that there is a question, feel
I
free
will
to
ask you.
stop me
Okay.
anytime. Don't think.
Okay.
Good.
Perfect.
Then, good morning, everybody. Thanks for being here to this lecture of this workshop. I think you have had quite an intense week and days already with learning a lot of stuff. And today I'm trying to give you a little bit insights on what we call lattice dynamics. So this is generally, we call them also phonons. And the interesting thing about lattice dynamics or these vibrations and solids is that they tell you a lot about thermodynamics and about how materials behave at different temperatures. And for that, let me start with what you probably have already discussed and heard even before this actual workshop. How do we discuss crystalline solids usually? So usually we think about I call it an idealized crystal structure, something that is very symmetric, and we describe that by a unit cell that is shown here in green, and the unit cell itself is described by lattice vectors. And then you have all periodic images, all copies that are exactly equal to this unit cell around around this one. So that spans really the whole space. And these lattice vectors are actually describing this symmetry, this translational symmetry. And mathematically, we write that down in that way. So you have basically one vector that is called Ri in blue here that describes the position of an atom in the unit cell. And then you can add all kind of lattice vectors to it, which will describe basically the copies where these atoms are sitting. And this is how you usually describe such a system, how you think about it, how you treat it mathematically. And for instance, if you use a DFT code, this is also the kind of input you give them. So you say, look, these are the lattice vectors. Here, it's a cubic lattice in that case. And then you have some atoms sitting at certain positions, and you give it this information. And then the code treats it. And you usually then feed this kind of information to electronic structure theory, so to the DFT code of your choice, and this gives you all kind of information about the system. So he solves the electronic structure problem. You've heard a lot about that in the last couple of days, and what is most important in this context, what you really get, is also the energy of the system. So what is the energy of such a unit cell at these positions, and the forces that are acting on this system, and also the stresses. The stresses are essentially the forces that are acting on the lattice vectors on the unit cell. And why is this useful? Or what do we use that for? For instance, we can try to map out here the energy as function of the lattice constants. Here in this case, this is we look at it for a tetragonal system where we have one lattice constant A and one lattice constant C, and then you get this kind of potential energy surface. And what you then typically do is that you also want to know what is actually the ground state structure. What happens is the minimum energy structure. And for that, you perform so-called relaxations that are numerical algorithms that are looking for this minimum. Remember, when you do a DFT calculation, in principle, you put in this one position, this lattice vectors, for instance, you get the energy and forces and so on, but only information about one point. And the relaxation algorithm then uses these forces and stresses to wander down the minimum. Now, this is not a perfect algorithm that does this in one step. It's an iterative procedure. For instance, you then jump from one, do again a calculation, then jump to the next, do a calculation, jump to the next, and at some point you find the minimum. And when you're at this minimum here, what you actually know is that the energy has reached a minimum. If it's a minimum, there are no more forces acting on the system. And so what we actually know is, and what we then easily tell, okay, now we found the equilibrium lattice constant and equilibrium positions of these atoms. And we would even say, look, if we neglect temperature, then this would really be the structure at 0, 0K. And this is how we often think about it. However, this is not totally accurate. If you remember back about your lecture of quantum mechanics, there should be something already coming to your mind. And if you think about what Werner Heisenberg would say, he would say, no, look, actually, we know that positions and momenta have to fulfill the uncertainty principle. What does this mean? That the atoms cannot actually sit like here in a perfect system, even at 0K, just sitting there. They always have to move a little bit. This is what we call the 0K or zero temperature fluctuations, which are due to this uncertainty principle of Werner Heisenberg. So, in fact, if you think about real materials, even at 0K, they do not look like that. If you would be able to make a movie, it would look much more like that. So everything moves all the time. Everything is wiggling around in the solid, like you see in this movie. And while on average the symmetry might be restored, actually, if you would look at single snapshots, the symmetry is never actually really there. Even this periodic symmetry is broken. And this has important consequences. And important consequences are what you often also call the failures of the static lattice model. That means these are problems or quantities that are not correctly described if you just stick to this picture of immobile nuclei that do not move. And this affects very fundamental properties. Even equilibrium properties at 0K, like lattice constants, energy, elastic constants, are actually affected by these motions. At 0K, that might be smaller, minor corrections, but they're still present and measurable. It becomes worse if you're not looking at 0K, but you go at a higher temperature, at room temperature, or even beyond. Then all of this stuff is much more influential. You will see lattice expansion. You will see that you have a specific heat of your system, and you can even see phase transformation so that one crystal structure becomes more stable than the other. These are all equilibrium properties, so really something that you measure on average. But there's also a problem describing so-called non-equilibrium properties. For instance, this includes charge transport. So in such a static nuclear model, you cannot describe electrical conductivity, superconductivity, and so on. So all this kind of charge transport does not work because nothing is moving. So also the electrons are not moving, everything is static. Same is for heat transport, which is essentially energy transport. So thermal conductivity, transmission of sound are not correctly described in a static model. And also the coupling of those, so what we call the thermoelectric Seebeck and Peltier effect, is not accounted for. And last but not least, even interaction with some form of radiation, X-ray, infrared, Raman, neutron, and so on, very much depends on the motion of the nuclei and cannot be assessed with just a static model. And we will try to give an overview a little bit how we can now address these problems with density functional theory and models that build on density functional theory. And for that, let me first really go back a step. What do we need actually to do to describe thermodynamics? And if you look at your statistical physics textbooks, you will learn that what you actually need to do to describe a system with n atoms, a certain volume V, and a temperature T, you need to calculate its canonical partition function. Or better, its Helmholtz free energy. So the Helmholtz free energy is related to the partition function like that. And you need to calculate basically this integral over the Hamiltonian of the system, both for that depends on the positions and the momenta of the nuclei. Now, this is a very, very complex integral because you really would have to calculate it for all possible configurations of your system, and this becomes unfeasible very, very rapidly. You can do 1, 2 atoms, maybe 3 if you're really putting a lot of computational effort in. But calculating this partition function of free energy in that way is extremely expensive because even configurations that are very high in energy will still contribute to this exponential tail. So what are we doing instead usually? What we do, we run so-called molecular dynamics calculations. In molecular dynamics, we again start with some kind of input structure. We feed that to the electronic structure theory code. This electronic structure theory code then gives us the total, the electronic density, but also the energy and forces. And now we don't use these forces to basically relax the system as we have done before, but we use these forces to solve the equation of motions, to look on how the system would move at a certain temperature. So we again update the geometry, but we do it in a dynamical way by integrating the equation of motions. And that allows us to explore the dynamics of atoms. So this is exactly how I've actually produced such a movie like that. So at each time step, you perform an electronic structure calculation, you get your forces, and then you can integrate up this equation, and you get the new position at the new time steps. And you have to do that one after the other. Usually you take something like a time step between 1 femtosecond and maybe 4 or 5 femtoseconds, and then you can easily integrate that up. Sure, you have to specify basically the initial conditions, and then you can integrate that up. Using a standard integrator, you get a microcanonical assembly in which the number of particles, the volume, and the energy is conserved. But you can also switch to other thermostats, and then you can even assess different kind of ensembles. The canonical, if you use a thermostat, you can use all kind of, for instance, a barostat to change the pressure instead of volume, and so on. But this would be electromolecular dynamics on its own. Here, just want to give you an idea how this actually works. The important thing that you have to remember here, however, is that what is feasible that way. If you think about the effects that we typically observe for such vibrations, they range, let's say, in time scales from few picoseconds to nanoseconds or even beyond. And also in terms of length scale from angstroms to nanometers up to microns and beyond. Now, if you want to do that really with first principles, you can try to do that, but you will have a problem because, as we said, each ab initio MD step has to happen at a time step of femtoseconds. So already reaching 1 picosecond requires thousands of DFT calculations. And if you then want to go even to nanoseconds, you need a factor of 1,000 more. And you cannot do that in a small system like in the unit cell, because we have seen this kind of effects expand well beyond the unit cell. You have to do that in much larger cells, which would make the calculations even more expensive. So to reach really this thermodynamic limit up here, to look at effects that last over nanosecond and range over microns, we need a fast, inexpensive technique, but that is still sufficiently accurate that we can build on the ab initio technique and try to assess this thermodynamics. So this already brings me to my first take-home message. Remember, everything moves. Nuclei and atoms never stop moving. Always when you assume that they're static, you make an approximation. That in many cases might be a valid approximation that is good enough to get some results within a certain accuracy. But if you want to know better, or if you want to look especially at thermodynamic properties, it is not sufficient to look at that. You have to also look on how the nuclei move. Good. How do we do that? I already said we need a better approximation and a better technique to address this thermodynamics. And since we are physicists, we use always the harmonic approximation. So we use basically harmonic oscillation. How do we do that for such a solid? Let me sketch that. So we start again by looking at our total energy surface. So in principle, as we've said, we have multiple atoms and multiple dimensions in our system. So this is a 3n dimensional surface. Here I'm sketching it as a one-dimensional because the concept is the same. So the first thing that we did and that we explained when relaxing on this potential energy surface, we discover where the equilibrium is. And that is good. That was the point where we are. But now we approximate this potential energy surface. And we do that by a Taylor expansion around the static equilibrium. Now, the first term in such a Taylor expansion is obviously the energy at equilibrium. So this indeed is the first term that enters this expansion, and this is what we would calculate in a standard relaxation. If we go one step further in the Taylor expansion, we need to look at the derivative of the energy at this position. Now, since this is equilibrium, the derivative has to be zero by construction. This is how a minimum and equilibrium position is defined. So this term vanishes in this system. So we have to go to the next term to get a non-trivial expansion. And in the next term, we have basically the second derivative of this potential energy surface with respect to the nuclear positions. And this then gives us basically a parabola. You already see now that this is quite a good approximation if we are close to equilibrium, but this can become inaccurate if you get quite away from equilibrium. And this is something that you have to keep in mind also later when we discuss and do these calculations in more detail. So this is just a warning. The harmonic approximation is only valid if we're really close to this equilibrium structure. Now, the problem is the concept, all that we have to do now for these phonons is calculate this Hessian. And this kind of property is not that easy to address, and we'll first try to think a little bit what the properties of it is and why this is so complex to calculate. So let's go back. What does this Hessian describe? Here we've seen that is essentially the derivative of the energy with respect to two positions, but using the definition of the force as negative derivative of the energy, we can also write it down as first order derivative. So how much does the force on atom I change if I move atom J? So how much would the force acting on this atom here, on the blue one, change if I move atom J? And one important thing that you have to remember that this Hessian has, the Hessian itself is pairwise translational symmetric. So if I look at the Hessian for these two atoms, it's the exact same entry as for these two atoms. So when moving this atom, the force acting on that will be the same one as the force acting on that when I move this atom. This is helpful. Because we can then restrict one index of this Hessian to one unit cell. So let's say the first one, the green atom, we only need to know what happens here. What are the forces acting on these atoms? We're not interested on the other because we can construct them. However, the second index, so this atom J, the one that we're actually moving, this is not translational invariant. And this you can also relatively simply understand. Obviously, if I move this atom, it will have a different force acting on here. Then I move this atom. Or if I move the atom over here. So we have to really look at all kind of atoms blue here to construct these Hessians. So the second index really runs over the whole infinite crystal. In other words, we now have an expression where this Hessian basically has one index I that runs over the unit cell, and then this index J that runs over the whole system. Now you will think, oh, that will be tricky because now we have to calculate stuff for in principle an infinite crystal that is will cost me a lot of time to go over all this kind of atoms J's in different unit cells. In principle, you're right. However, you also can assume or think that actually the interactions in the crystals will decay quite rapidly with distance. Think about it. If I move this atom, I will definitely have some force on this atom. But if I get farther and farther away, for instance, this atom, this will have not so much effect. And at some point, the farther I go away from the actual atom where I'm looking at the force, this will become zero. And this is helpful because that means that we have only a finite number of force constants or entries in these Hessians that we need to compute, because after a certain distance they will become zero. And this makes this problem tractable at all. So far we have been stuck to very fundamental mathematical properties of this Hessian. Now let's try to go a little bit deeper. We now really want to compute these harmonic force constants. And this is quite challenging. And why? Again, we have to look a little bit what happens in quantum mechanics.
Dr. Kristen?
Yes, sure.
Hello, hello. Can you please go back to the previous slide?
Yeah, yes. Let me check. That should be why doesn't it?
Talk about Hessian and the movement of the atoms and the relation between the movement. You are talking about the naturally moving atoms, like not from external perturbation or something, or
Yes,
yeah, this is the naturally moving, the vibrations of atom, not like
exactly.
something from outside.
This
No.
is at the moment I'm still talking about equilibrium. This
Okay.
is everything just the normal motion. Now, if you have a certain temperature, this is a thermodynamic motion.
Okay.
But even if you go to, let's say, 0K at zero temperature, you know that quantum mechanics does not allow anything to stand still,
Okay.
because this would violate the uncertainty principle.
Okay.
Neither the position nor the momentum can be zero.
Yes.
So even at 0K, there will be a small vibration still going on.
And this is valid for like wide range of temperature of or I think if it's wide range it will be an external perturbation, but it's like the normal, right?
It's in principle valid for all kind of temperatures. At some point, the solid will melt, and then you will have no longer a lattice. You will
Yeah.
have a liquid moving around, but this is valid really from 0K to whatever temperature you like. The atoms will be always moving.
Okay. Thank you very much.
No problem. Good. So, yeah, where were we? Okay. How do we calculate energy and forces and Hessians in density functional theory, or more generally, even in quantum mechanics? You know that in quantum mechanics, your energy or potential energy is given by the expectation value of your Hamiltonian with respect to the kind of wave function at fixed nuclei. If you now want to calculate forces, what you need to do is do the derivative of this potential energy surface. Now, it turns out that if you do this derivative, you get three terms. Basically, what you get is the expectation value of the derivative of the Hamiltonian. And then you get two terms in which you have the derivative of the wave function inside. Now, interestingly, you can show that these second two terms vanish. Why? Because the Hamiltonian acting on the wave function gives you its respective eigenvalue, and then you basically just get the derivative of the normalization condition, and this vanishes. The normalization has to be retained. So what this tells you is that the forces are an expectation value of the wave function and do not depend on the changes in the wave function itself. It's a very fundamental kind of result, the so-called Hellman-Feynman theorem, because it tells you that you can basically compute forces or how changes in energy without knowing what happens really somewhere else. However, this becomes more complex if we're trying to compute the Hessian. For the Hessian, we now only have to compute the derivative of the force with respect to the position. We apply the same kind of chain rule again, and now we get, again, similar terms. One term in which we have the expectation value of the second derivative of the Hessian. And now we have again two terms that have the changes of the wave function here inside. And here, this is not with respect to the Hamiltonian, but to the derivative of the Hamiltonian. And for this exact reason, these two things do not vanish. And we have to explicitly calculate the derivative of the wave function. This is called the response of the wave function to a nuclear displacement. It is also called electron-phonon coupling. And you can play this kind of derivation in a more general kind of fashion, and then you arrive at the so-called 2n+1 theorem, and that tells you that if you want the 2n+1 derivative of the energy, you need to calculate the nth derivative of the wave function or the electron density. So, for instance, if you have the zero derivative of the wave function, so just the basic wave function, you get obviously the energy and then the first derivative, that is the forces. If you have the first derivative of the wave function, you then get also the second and third derivative of the energy. And this is how you can do that. Apologies. Good, so there's some way you need to calculate these derivatives. We'll dive into that a little bit later as well. There are some ways around to that. One thing that you can do to avoid that is to stick to the forces and just calculate the Hessian by using finite differences. So what you do, you really calculate the forces acting on these atoms by displacing individual atoms. Now, this is a relatively straightforward approach because it's not that complicated to do. It works with all kinds of electronic structure methods as long as you have forces and energies. So you just need to construct your geometries, move one atom after the other, and then you can calculate these derivatives for the small displacements. So it can even work with high-level electronic structure methods for which, for instance, neither forces nor Hessians are really implemented. And it's in principle trivially parallel because it's all individual calculations for individual displacements. So this is straightforward to do. However, it requires explicit supercells, so you have to go to large systems, in principle, as we exactly as we showed in the previous slides and discussed, to have to larger and larger cells. And numerical noise can affect low symmetry system. This is a numerical technique, so you have to be careful in choosing this displacement right to get reasonable results. And then there is a second technique, the so-called density functional perturbation theory, where you get this result analytically. For that, you really evaluate this kind of Hamiltonian that we discussed before. How do we do that? Let's go for that step by step. So first, I write you down the cone-sham Hamiltonian as you know it. So you have your kinetic energy, your external potential, your Hartree potential, and exchange correlation potential. That gives you this eigenvalue problem. And now, again, we do a Taylor expansion. But now we do a Taylor expansion really in this electronic Hamiltonian with respect to an external perturbation. In our case, this would be such a displacement. So what do we get? For each of this property, we now get a Hamiltonian that is the original Hamiltonian plus the derivative time the displacement. Same for the wave function, same for the eigenvalues. For the sake of simplicity, to really distinguish that, instead of writing explicit derivatives, this is often written with this index up here where we say zero derivative, first derivative, and so on. Now, using that, we can plug that in back in our actual equation, and then by plugging that in the actual Contram equation, we then get the so-called Sternheimer equation. And this resolve basically tells us how to calculate this perturbation. Look carefully. So now we have basically the original non Can-Sham Hamiltonian and eigenvalues here. Here we have the perturbation. This basically couples to the actual original wave function. Here we have the response or the derivative of the wave function. And we can solve this Sternheimer equation essentially by again finding an approximation for this wave function. So you can expand, for instance, your wave function in terms of the equilibrium wave functions, or you can even expand it as function of your original basis functions. This is the so-called self-consistent field, coupled perturbed self-consistent field method. But formally, it's exactly the same. It's just different waves to solve the exact same equation. And then you can find an iterative way to basically solve this equation and get the responses. So in practice, what this means, you first have to run your standard DFT calculation. From this DFT calculation, you get your equilibrium properties here. And using them, you can then run a second self-consistent field run that gives you the perturbation. One important thing here is that you also get a normalization condition both for your original wave function as we know it, but then a second one for your actual response. And one thing that this implies is that you can introduce perturbations that are extended, that carry an own wave factor. And this is nice because you then can work in the unit itself without going to supercells. So what does that mean in practice? Again, as explained before, the standard kind of procedure would be to run your density and functional theory calculation that gives you a very nice periodic density. And then with that, you go into your perturbation theory loop, you calculate all the responses, and this gives you then the density of wave function response. Look at this. This is no longer a periodic kind of property. Here, obviously, the response is centered around the perturbation. So here we have moved this yellow atom here. So obviously, we see the most change in the electron density around this atom. And once you have calculated all of this, you can calculate the phonon properties. And here I give you just an example from my own work where we've implemented that in an auto electronic structure code in FHI Ames. And we've benchmarked that both for finite systems, so for finite something like a C60 where you get some frequency spectrum, but also for periodic system like silicon, and then you can compare how this works. And this is a very accurate technique to get very nice results. So let me get back shortly here. What to actually calculate here in this response, I mentioned before, this is the so-called electron-phonon coupling. Formally, this is also defined already by going into reciprocal space. We will discuss that a little bit more later, how this is exactly done. But these are basically the property that you then also need for more advanced electron-phonon coupling calculations. And an important thing here is to remember, since this is a localized thing in real space, it is using delocalized properties to describe it is not particularly efficient. So one thing that one usually does when doing such perturbation theory calculations is that you first compute your property on a finite Q-grid on very few points in a reciprocal space. Then you do a Fourier transformation to real space. There it is easy to interpolate because these things are localized. This is what is usually done with Wannier types of codes. And then you can Fourier transform back to reciprocal space and really cover your whole Brillouin zone. And this, in the end, then gives you the properties that are needed to really get all this explicit response. Calculate these Hessian properties. Good. Now, I've given you trying a little bit an idea how these methods work. You will learn a lot more about these density functional perturbation theories in today's hands-on exercises where we will exactly use this technique to calculate properties for silicon, and you will see in practice how this works. Again, the advantage, this system works within primitive unit cells, so you don't have to go to expensive supercells. But on the other hand, you have to do individual Q points, and you get a lot of information because you really get full access to electronic perturbation, not just to the Hessian as it is the case for finite differences. The disadvantages is that it requires actually quite some work in implementing it, especially if you go to more advanced exchange correlation functionals, because then you have to do the derivatives of those as well. And this is far from trivial for a programmer to implement that. And it is quite costly because it scales unfavorably with the number of atoms. So if you're dealing with a large system, it can be quite expensive to do that. Good. Now, this already brings me to my second set of take-home messages that I want you to remember. As we said before, everything moves. The nuclei are always moving. So we have to describe how they're moving. And to do that, using the full energy surface would be much too costly. So what we do, we approximate this energy surface on which the nuclei move. And that we do using a harmonic potential, basically a parabola that approximates this potential energy surface around equilibrium. And with that, we can then describe the dynamics. And this is what we will discuss in the following. For the time being, we've now discussed how we can get such a harmonic potential by calculating the second order derivatives of the potential energy surface at equilibrium. Good. Do you have more questions on that part? No, I don't see any. So let's try to get one step further. We discuss shortly the thing before we then switch into the break. Good. So far, we have now described our energy by this harmonic parabola. Basically, here we have a sum over all atoms, a sum over all unit and supercells. We have the Hessian that we calculated, and now we just have the displacements from equilibrium here. The respective forces would look like that. And so do this actual equation of motion, which we relate basically acceleration on the left. This is just a Newtonian equation of motion with the actual forces acting on these atoms. Now, we can play a little trick, as we usually do, because we've seen that essentially there is still some symmetry in this Hessian inside. What we can do, we can describe the displacement at different lattice side by essentially a Bloch-like expansion. So we say actually the displacement at a certain atom J in different unit cells is related to the displacement of atom J in the unit cell times this phase vector that is driven by the actual lattice vector. If we put this kind of stuff in this equation, we get this simplifies a little, and we can then put essentially all phase vectors on different sides. And what we then get is an equation for the derivative of the displacement in the unit cell with this quite of complex kind of structure. We can simplify a little bit more, as we discussed before. We don't need to know every kind of entry of the hash, and it's sufficient to know the one in the unit cell. And if you look a little bit more closely, in the end, what we end up is an equation that describes only the displacements in the unit cell with respect to each other. This matrix coupling those two is the so-called dynamical matrix that has this form. But there has been a much important step that we've done here. Up here, we had an infinite number of degrees of freedom. So because we were looking at the equation of motion for all atoms for the full solid. So for the index I in the unit cell and all periodic images described by the lattice vector. By doing this transformation, now we have transformed this problem to the problem of just the atoms in the unit cell. So we now have a finite number of degrees of freedom. There's a downside. Now, however, this matrix has a dependence on Q. So we have to solve this problem for all Q points in the first Brillouin zone. This is very much the same thing that you've also done already at an electronic structure theory level when you introduce Bloch wave function to deep periodic solids. Also in that case, we had in the beginning an infinite number of electrons, and we reduce that to a finite number of electrons in the unit cell. But then we have the additional complexity that then we get a Hamiltonian that is k vector dependent, so that also depends on the k points in the first Brillouin zone. And this is the exact same thing that we see here. So we have to address this at all q points in the Brillouin zone. The nice thing is we can do that relatively easily. If you look at this equation, you will see that is actually an eigenvalue equation. You can do an ansatz that again, this uj here is essentially a harmonic oscillator. You plug that in and then you get an explicit eigenvalue equation. And this can be solved and you get 3MP solution where you get basically this frequency squared and you get the eigenvectors here that actually describe your motion of the system. And the only thing that is not known here are the complex amplitudes that would be determined by the initial conditions. Let me shortly explain what this really means in a very simple example. Look, here we have one system, a linear chain. This is very simple. So we have here a unit cell with two atoms and one lattice vector that describes the periodic images. If we would work in real space, we would have a Hessian with infinite entries, because obviously the force acting, for instance, on this black atom depends very much on which atom moves everywhere. By Fourier transforming that, we get a dynamical matrix that only depends on these two atoms, but has an additional dependence on Q. Remember, we can do that because we know that the Hessian actually becomes zero for large lattice vectors, because we've said before the interactions decay for large distance. And this allows us to calculate this out of this Hessian with finite number of non-zero entries, the dynamical matrix for the whole reciprocal space. So we have this dynamical matrix, we have this eigenvalue problem, and then we get a solution of that. What is the solution? Typically, we plot that as vibrational band structures. Again, conceptually, it is the exact same as you did in electronic structure theory. We plot the eigenvalues of this equation as a function of the wave vectors as along a certain path. Now, however, we are not dealing with electronic energies anymore. We're dealing with vibrational energy. And let's look at some properties of that are very general. If we look at the gamma point, that means that our Q vector is 0. We're looking at the center of the Brillouin zone. Then this kind of exponential obviously becomes 1 because it's the exponential of 0. We have to solve it. And the solution at this point has some very distinct characteristics. More generally, we see here the kind of chain and the phase vector that is constantly 1. Here is a red line. And we get two kinds of solutions. One is the so-called acoustic mode, here in green. In this acoustic mode, all atoms move in phase, both in the unit cell and, due to the fact that the phase vector is 1, also across all periodic images. In other words, what this means, if you look at the arrows, this would just mean that you just move the crystal across space, all atoms equally. Now, moving the crystal across space does not cost you energy. And this is why these acoustic modes are always 0 at gamma. Then you have a second solution. In the second solution, these are the so-called optical modes. What is the difference? You see, here the atoms within the unit cell vibrate against each other. Still, the actual periodic images are in phase. So all unit cells behave the same way because the exponential here is 1, there is no relationship between here. But due to the fact that the actual optical phonons vibrate against each other, we now get a finite vibrational frequency here. And these are the so-called optical modes. Good. What happens somewhere else? Look here at the border of Brillouin zone. That would be the X point in this case. Now here we get a phase in which we have an alternating phase. So basically, each adjacent unit cell changes sign. What does this mean for our phonon modes or at different positions? Look at the acoustic modes. Now, this would mean that in the first unit cell, the acoustic modes point in the right direction, but in the second unit cell, they point on the opposite direction. Then they point again in the original one. This is described by this exponential. For this reason, we now have a vibration of these two unit cells against each other. And this is reflected in a finite vibrational frequency now also for this acoustic mode. And you see the exact same behavior here for the optical modes. Now, in that case, we have the exact same motion in the original unit cell as we had before, but now the adjacent unit cell has exactly switched motion. So now it goes in the other direction. Here, the change is not so drastic. So what you actually see is that the optical modes behave very, very similar and have similar frequencies as they had at gamma. We can even generalize that and look at what happens if we go to different Q points. So again, now we had just discussed the border of the Brillouin zone in which the phase changes or becomes periodic over 2 unit cells. If we get closer here to the in the middle between gamma and X, we now cover 4 different unit cells. If we would go even closer to gamma, we would then start covering 8 unit cells. If we then get even closer, at some point we get 16 unit cells. And see, if we go further and further this limit, at some point we reach back gamma, where this is totally flat. And if this is totally flat, we can then again stick to this unit cell condition as we had in the very beginning, where we discussed this gamma point and said that everything is in phase and similar. So to sum that up, what do we actually get for atoms in a unit cell? We always get 3 acoustic modes. 3 acoustic modes that they are in phase within the primitive unit cell. They vanish at the gamma point, and close to the gamma point, they show a strong, typically linear dispersion. So you see here, this behaves linearly here, and actually this typically is related to the speed of sound in a solid. On top of these 3 acoustic modes, we get 3n minus 3 optical modes. This describes vibrations in which the atoms in the unit cell vibrate out of phase. The frequency is always above 0, even at gamma. And what we then usually see is a relatively weak dispersion as sketched here. Can give you a real example, and this is what you actually would also calculate this afternoon. Look at diamond silicon, so standard silicon as it's used in semiconductors. And we can do that at different levels of theory and then interpolate between these Q points. So here, this is the result I get from a primitive cell, or when only looking at the gamma points, so only looking at 2 atoms. Then I would get a dispersion that looks like that. If you get to larger cells or to more Q points and do the interpolation, what you see that you get quite a different result, but the gamma point has not actually changed because we have retained that in our calculation. We can then go even further and look at the 4x4 cell, or here looking at 4x4x4 Q points, and then interpolate between. We see that the results gets even better because we've now covered more reciprocal space. And here I'm now going to even a 6x6 cell, or quite a strong Q grid that we're covering here. And we have now essentially achieved convergence. So just to remember a little bit, look at this kind of plots. Here we're looking at the frequency in terahertz, but 1 terahertz is 4 MeV. So the actual difference you observe here are really, really minute. So we're really close in convergence here and get a very nice converged result. And you also see quite nicely here the different type of acoustic modes here. So here you see that we have 3. In some cases, some are degenerate because of the high symmetry of silicon. You really nicely see also the optical modes that sometimes are degenerate and sometimes not. So everything works out nicely. And with that, let me just compare to experiment. If you look at this kind of result and compare it to an experimental measurement of this thing, you see that we get a very nice agreement with actual experimentally measured phonon band structures. And this is principle a very nice success story of density functional theory also in general, because if you think of it, to measure this kind of properties, what you actually need is a neutron reactor. So something like a multi-million, if not billion machine that needs to be built and cared for and retained to actually measure this thing. And calculating this can be done on your laptop, and is actually also the topic of the tutorial that you will have this afternoon. Good. I think we have now covered this silicon example. If you have no more question, I would suggest sure, come in.
Yes. My question is about if you apply a pressure, what will happen to the phonon?
I mean, it will change because we have now done that at a very specific lattice constant. So you can then change the lattice constant, and then you can do your calculation again. And then you will see that your actual phonon frequencies change. Indeed, that would require an additional calculation. What you would usually see is that if you apply some pressure or strain, that for pressures at least, if you apply some pressure, that the phonon frequencies go up. Why? You push the atoms more together, and that naturally implies that the interactions become stronger. So also the atoms are more confined and are in parabolas that are, stiffer. On the other hand, if you expand your crystal, you would expect your phonon frequencies to go down. This is a general rule of thumb, and it's not always like this. Maybe to the end of the next session, we can even go a little bit more in detail, because this is closely related to what happens during lattice expansion. Because if you heat up your crystal, you would actually expect it to expand, and this is closely related to how the phonon frequencies change with lattice constants and such with pressure. Does that answer your question?
Yes, very clear. Thank you.
Good. So very good. I mean, think about a little bit. If you have more questions, you can also ask them when we start again back in 5 minutes. I would just grab a coffee and then see you again back here in 5 minutes.
Okay, so
Thank you for your attention so far.
thank you.
Hi, Kristen.
Hi, Musa.
How are you?
I'm very good. How about you?
Good, good. Actually, I have two questions.
Sure.
About the phonon dispersions. In some materials, you'd see like a clear gap between optical mode and acoustic mode.
hmm
And people, when they study some different system and they'll, if it axial strain or pressure, you see this gap changing and also within the density phonon dose. What
hmm
does this really gap means?
I mean, what this reflects typically
Yeah.
is that you have quite some difference in binding. So think about here the diamond example we've shown here. This is silicon that is equally bound against each other everywhere. So here you basically mix up everything because in all direction the system looks relatively equal. I think maybe I switch already to the next slide because you will see it a little bit there. In magnesium oxide, which is an ionic crystal, you already see that yes, there is one optical mode that is close here to the acoustic one, but then the other one is quite much higher in energy. And this, for instance, comes from the fact that this is the magnesium and the oxide oxygen are different atoms, and so they are much closer bound to each other, and so the bonding is stronger. And this, for instance, uh, gets even worse if you go to, let's say, a more complicated crystal. Think about an organic crystal. Then you will see that, for instance, the if you have this crystal built out of individual molecules, uh, the vibrations within the molecules, they will be optical and they will be very strong because the molecule itself is strongly bound. But the acoustic modes, they're essentially driven by van der Waals, and for this reason, they will be much softer and much thing. And this will then give you a gap between this acoustic and optical modes. This is, in principle, the physical reasoning that you see there. Does
Uh,
this answer your
yeah, yeah,
question?
yeah. It makes sense. It makes sense. Thanks. Now my second question actually it might not be related directly because this is crystalline. I am more interested nowadays in amorphous materials.
hmm
And as you know, we don't have translation symmetry there, so we can talk about the K space.
hmm
Do you know a better way of looking at the phonons in the amorphous material?
Yes, in principle, I mean, it depends a little bit how weirdly amorphous it gets. The problem really is in with this kind of amorphous systems, you lose this K space, so you lose also this concept of a phonon like as a lattice vibration because you no longer have this lattice. What you then really have to do is basically take quite large supercells in the same K in the same spirit as we discussed before, because even to just model the amorphous character, you already need a large cell, and then you do just essentially the vibrations at the gamma point. And if the system is amorphous, this will then converge to a density of state where basically you only have this kind of vibrations at the gamma point. So speaking of dispersions, if you would really calculate something like an amorphous system in this kind of methods like here, what you would get is basically dispersions that are just flat. So you have one frequency at gamma, and then it's flat across all reciprocal space. This is what it would show you. The thing obviously is that in this kind of amorphous system, since you cannot exploit reciprocal space, the calculation get more expensive.
Yeah, I see. I see. Thanks.
Good. Do we have some more question? if not, I would start again. So, and exactly now switching a little bit to essentially the second topic that you will have also today, when we in the hands-on tutorial, where you'll be talking about polar crystals. And as already mentioned when discussing with Musa, here we're looking at magnesium oxide. And what you see actually is, compared to the silicon before, there is something wrong here. Experiment tells us that this optical mode is going up here, while our calculations do not show anything here. So what is going on here? Here we have a little bit of a problem. When you have charged atoms, that is what I mean with polar crystals or ionic crystals. So you have, like in magnesium oxide, you have the 2+ magnesium and the 2- oxygen. When you move them, a weak long-range dipole field is induced. So basically you have a long electrostatic field. And this is a little bit problematic because this is a long-ranged field. And in DFT calculations, where you essentially use a small unit cell or a small supercell, this is clouded by all other forces and is not actually included, because you cannot include such a long-ranged field that breaks the symmetry. But if in the real case, when all other forces have decayed, in the long range, this interaction becomes significant and noticeable. So we have to find a way to account for these interactions. And how can we do that? We do that by calculating the Born effective charges, which are essentially the derivative of the polarization. And in layman words, nothing else than basically the nominal charge of this atom. So for magnesium, you would get something like around 2+, so maybe 1.97+. And for oxygen, you will get minus 1.97 as a charge. Then you can calculate also the dielectric constants. This tells you how the electric field generated by such a displacement is screened by other atoms. And then with this information, you can basically construct the electric field acting in that system at variable Q points. And then you can add that in hindsight to your dynamical matrix. And with such an expression that essentially covers this kind of interaction as function of the Q point and as function of your Born effective charges. And if you add that to your dynamical matrix and then diagonalize and solve the problem again, what you see is that you then now get a much better agreement experiment. So if you compare now the two kind of things, first we had this kind without correction, and now with correction we get this correct kind of thing. And this effect is basically what we call the LOTO splitting, because this is the difference between so-called longitudinal optical modes, in which the displacement is aligned along the k vector, and the transverse optical mode, in which the actual displacement of the atoms is orthogonal to the propagation direction, again along reciprocal space. Good. And this has now, you have everything that you need to know to calculate and understand such vibrational spin structures. And this is nice because you already can get a lot of insight on how the vibrations are acting in the material. However, we don't do these calculations just for calculating something like a band structure to compare to experiment. We want to learn more about it. So the vibrational band structure is not the only thing that we want to know. What we typically also like to calculate is the so-called density of states. This is nothing else than the integral over this band structure, where we actually count how many vibrations or vibrational modes are present at a certain frequency. And you can rewrite this integral over a delta function, essentially as an integral over the surface where you're looking at the gradient of this thing. And then you essentially get different peaks. It tells you where actually phonon modes are. So if you compare it or think about of the band structure before, here we have this acoustic region with this typical kind of increase here where we have very few frequencies around zero, and then we start getting some modes. And typically where we see some peaks, that is exactly where we have a strong presence of optical modes, because this is exactly where we have a flat dispersion. So for instance, think about here where we have something like at around 500 centimeters. If we go back, this is exactly basically this modes here where you see a strong peak then in the density of state. Good. We have now obtained ways to describe this 3n independent and q dependent harmonic oscillators, which can we and the most important thing here is that we can now solve the equation of motions for this harmonic oscillators analytically and exactly. And this provides us now a route to go towards the actual thermodynamical motion. So here you have to be a little bit careful. If you think about classical physics, then classical thermodynamics would give you the equipartition theorem. So each mode would exactly carry an energy of kBt in a thermodynamic equilibrium. If you, however, think about the quantum mechanical solution of this problem, you get a Bose-Einstein distribution. Then each mode carries an energy of h bar omega times the Bose-Einstein population plus 1/2, where this 1/2 exactly describes the zero-point motion. To better understand it, let us look for a second on how this kind of energy for each mode depends on the temperature. Oh. In the classical limit, we have a constant behavior. Regardless what kind of frequency this oscillator has, it has zero energy at zero temperature and then increases linearly. So the higher the temperature, the more energy each of this oscillator has, regardless what its frequency is. If we switch to the quantum mechanical picture, however, we have a distinct dependence on the frequency itself. If we have a rather low frequency, we see that this does not much change from the classical picture. Actually, the difference are only vary in this low temperature regime, where we see that this factor of 1/2, the actual 0-point motion, gives us an energy that is already present at 0K. If we go to modes that have a little bit higher frequency, around 15 terahertz, we see that the 0-point motion is much more present. So look, this at least survives until 200 or even 300K, and to really reach the getting close to the Clamp-Meslica limit, we have to go to very high temperatures. And this becomes even worse if we go to higher phonon frequencies like 30 terahertz and more. So there, the 0-point motion dominates even at very high temperatures. If you now compare that to the vibrational motion we had in silicon, you see here we had optical modes already that were around 15 terahertz. So silicon is already a case where some of this quantum mechanical motion is still alive at 300K. And if you think about organic crystal, or especially crystal involving very light atoms like carbon or hydrogen, Here, frequencies can reach up to 60 terahertz or 3000 centimeters inverse. So here you would really have a case where hydrogen behaves quantum mechanically well beyond room temperature. And this is an important effect that we need to account for, and you have to keep that in mind when doing your calculations. So for the following, we will keep that in mind and use this quantum mechanical statistics also to calculate everything else. So, and the first thing that you can calculate using this harmonic approximation is, for instance, the harmonic free energy. Here, as we discussed in the very beginning, the first thing that enters is the static equilibrium energy. Then you get the contribution from the 0-point vibrations. You see exactly the factor 1/2 that comes in here, times the frequency of the phonons, times the density of states. So here the density of states allows us to account for each of the harmonic oscillators that is present in our system. And then we have a third term, the thermally induced vibrations, that now exactly also depends on the temperature. So we can now calculate this in this form because we can solve the equation of motions analytically. And then we can integrate up these equations. And for instance, we get the free harmonic energy of the system. What you see, this decreases with temperature, giving us a distinct thing. And we then can also calculate the specific heat. And the specific heat is essentially the second derivative of the temperature with respect of this free energy. And you see you get a distinct dependence here. You see here at low temperature, we have a cubic dependence on the temperature that then goes over to something exponential and then flattens off and becomes static in the classical limit. And if you remember your classical lectures about statistical physics, you know that actually the specific heat in classical physics is so constant, and you have essentially a number of degrees of freedoms times kb contribution for each degree of freedom. And this is exactly what we reach at high temperature. In silicon, we have 2 atoms and 3 dimension. So we have 6 kb of specific heat in the classical limit here, according to the Long-Petit law. And everything that you observe here are really quantum mechanical effects of the nuclei that describe how the specific heat changes. This harmonic free energy is not only useful for calculating something like specific heat, but it's also useful, for instance, for looking at phase transformations. Here, I'm looking at one example, that is the phase diagram of zirconium oxide. If you look at it experimentally, you know that you have different structures. At temperatures below 1200 degrees Celsius, you have a so-called bedellite, a monoclinic structure. If you go to higher temperatures, if you heat it up, you end up in a tetragonal structure. This is a little bit more symmetric, but it's still tetragonal. You see the oxygen atoms are pairwise displaced here. If you go into even higher temperature, what you reach is a cubic structure, a so-called fluoride structure, in which all atoms essentially are on high symmetry position of the atom. Let us focus on these two structures first, because we want to describe the phase transition between those two. How can we do that? First, obviously, we would calculate the relaxed energy at 0K. And what you would discover is that the monoclinic energy, the ground state energy, is lower than the actual tetragonal energy. And this would tell you that at 0K, the monoclinic has to be stable. But this does not tell you anything about when you have a phase transformation. For accounting for the phase transformation, we have to calculate the phonons as well. Now, here I've done that both for the monoclinic structure and for this tetragonal structure. I think you nicely see here that the monoclinic has lower symmetry and so more atoms in its unit cell. so you get actually more modes in this band structure. Here, the tetragonal one would have a smaller unit cell that is shown here. By symmetry, you can reduce it by half by taking just half of this thing. And then you get a band structure that looks like that, and that also has fewer optical modes and so on. Now, we again switch to calculating the free energy, again using the electronic contribution, the zero permanent point vibration and the thermally induced vibrations. And then we can look on how these two free energies differ from each other. So this is the free energy of the tetragonal minus the one of the monoclinic structure as a function of temperature for two different DFT functionals, one for LDA and one for PBE. What you see is that both functional actually predict that the monoclinic one is stable at 0K. So, and you see, if you even would prolong that and ignore something like 0-point frequency, this would not be affected in this case. In some crystals, especially in organic crystals, where these 0-point energies are much more prominent, this could even change the stability at 0K. This is not the case here. What we see, however, is that if we go up in temperature, the tetragonal structure becomes more stable. For LDA, we see that this free energy switches sign, and so the tetragonal structure becomes more stable at around 800K. Conversely, if we go to PBE, we see a qualitatively similar behavior, but the transition happens much later, only at 1800K. So what you learn from this is that actually also phonons can depend quite a lot on your functional. So you have to be careful in choosing your functional so that it really gives a realistic physical description of your system. But then you can actually describe phase transformations, I would say, quite well. You have to think about it. Here, experiment would give you something around 1400, 1500K for the temperature of the phase transformation. And if you think 300K are essentially only 25 MeV. So this is a relatively small energy difference or energy error that we see here. So this also tells you that when calculating these things, you have to be careful and you have to converge accurately, not just in the exchange correlation function, but also in all other properties to get a nice result. But this gives you now a route to really describe something as complex as a thermodynamic behavior of a material as a function of temperature. And since we had these questions before, obviously in this example I've only looked at the temperature, but you could do exactly the same calculations also as function of pressure. So looking at the system, at the free energy, at different volumes, and then you will get harmonic free energies that depend both on temperature and volume, and this would give you then information how this would change as a function of pressure and temperature as well, and how you can drive the phase transformation by applying pressure or not. Good. So far we have now gone over all this nice harmonic approximation. We started by discussing that all nuclear atoms move. We've shown that we can approximate the potential energy for this surface by using a parabola in the so-called harmonic approximation, that we can solve these equations analytically in this parabola, and this can give us now estimates on the thermodynamics. Still, we have to remember that the harmonic potential is an approximation. As we've shown in the very beginning, this is an approximation that holds well when we are close to equilibrium. But if we get far from equilibrium, this approximation can get bad. And that implies that we get errors. And deviation from this harmonic approximation we usually call anharmonicity. And these are effects that can become important and that have to be accounted for. I give you an example by sticking to zirconia oxide. If we now want to describe this tetragonal to cubic phase transformation, we now need also to calculate the cubic zirconia structure. If we do that, calculating the phonon band structure, what we get is a so-called imaginary mode here at X. What does this mean? This tells you that your actual structure is not even stable. So what you have is essentially an eigenvalue that is negative, and if you take the root out of it to calculate the frequency, you get an imaginary frequency. In other words, if you look at the potential energy, the cubic structure is sitting here not at the minimum of the potential energy surface, but at the maximum. And it would actually like to relax down to one of these two minimas. You can go a little bit more into the structure and analyze that. And what you really see is that the cubic structure is really the maximum here of this potential energy. And then you have to symmetry equivalent tetragonal structures in which the accident displacements are happening basically along different directions. And this is where the system would like to go down. So this cubic structure is not even stable here. And if you have such imaginary modes, the harmonic approximation breaks down completely. Why? Because obviously, if you have a parabola like that, this would point down to minus infinity, and your atoms would like to go down there. And this is then reflected also in your harmonic free energies. If you would calculate again the harmonic free energy for the system, here I've done it just for the LDA case. If you just look at the harmonic free energy, the tetragonal kind of structure would be always stable across all temperatures, and we would never have a transition to this cubic kind of system. To get a phase transition to this cubic kind of system, you have to account for these anharmonic free energies that go beyond the actual description that you have in a harmonic system. This typically requires to use molecular dynamics, expensive molecular dynamics, to really account for this kind of effects. But if you account for them, then you get a free energy that is actually lowered, and then you get a phase transition at this kind of point here. Again, here we've done that at LDA. We see that at 2200 K. That is, again, not in too bad agreement with experiment. And to get a more hand-waving approximation of what is happening, what you would actually see if you could make an atomistic movie of the system, what you see is that at low temperatures you have this oxygen atom that is sitting in this minimum, and if you heat it up, it starts wiggling around, wiggling around, wiggling around. And if you have enough energy to overcome this barrier, this atom would be jumping around between these two minimas. And what then happens is that it has so much energy that it does that all the time. And if it does that all the time, on average, if you would measure its position, you would say on average it is sitting here in the middle. Although, in fact, the actual energy or potential energy for the system is never really stable. This is just an average high temperature measurement. This is the explanation of this kind of phase transformation that you see here. Good. This has basically brought me back to the very basics that I wanted to tell you for phonons. Do you have questions so far? Otherwise, I would tell you a little bit more about anharmonicity as well. If you're interested or not, just let me know. Do we have questions?
For the participant, if you have a question, you can also write it in the chat and I will read it. Also, if you want to ask any question now. There is a question in the chat by Abu Sandal. He's asking, why does harmonic free energy decrease with temperature, or decrease with the temperature? Why?
I mean, this is essentially what, if you look at the actual equation for it, because you have essentially this kind of logarithm where you have basically this 1 minus this exponential that gives you this kind of decrease. So free energies always decrease with temperature, because obviously you start getting this motion. The atoms move, and they move more and more, and so you're including more and more entropy, and the entropy decreases your free energy. If you look at, it's basically U is minus the entropy times minus the entropy. So if you compare that with increasing temperature, you can move more, and so you stabilize a certain structure. But what really matters, and this is maybe what you have to keep in mind, energies and also free energies are not that meaningful, because they always depend on how you choose your zero energy and how you do that. What is really important is essentially how difference in free energies relate to each other. So, for instance, if you think about the phase transformation where we looked at differences between different structures, there it's important to know if it increases or decreases, because it tells you which phase becomes more stable and less stable. Or, to give you an example, if you go back to the specific heat, so what you see here, this is essentially telling you how much energy you have to put in your system to increase the temperature, and this is basically the second derivative of the free energy, or the derivative of the entropy, and so this has respectively to show such a behavior. I hope this makes it a little bit clearer.
Thank you. There is also Nihat. Nihat, you can open your mic and ask your question.
Hello.
Hi, Nihat.
How are you? I have a question about phonon dispersion curve of silicon exactly. I just want you to explain it more for me. The gamma.
What this means? So, what does such a Nihat? What does actually such a vibrational band structure tell you?
Yes.
So, it tells you the energy of the vibrations, or in other words, if you go back to the simple parabola picture we had, you say you look at a certain vibration, and then you fit the energy with a parabola, and what is the curvature of this parabola. This is essentially what it tells you. So here, for instance, let's first look at gamma here. So here we have an optical mode. This is really one silicon in this unit cell vibrating against each other. And if you would look at the potential energy surface of this particular motion, you would see that it has a curvature that corresponds to this frequency or energy. Okay? Now,
So the aquatic modes are 0 in gamma.
Optical modes are this. Optical modes are here.
This is the optical modes, and at 0 they are the
acoustic modes.
Acoustic modes. They are 0 because of?
They are 0 because acoustic modes means that all atoms in the unit cell are moving in the same direction. This is what acoustic means. And gamma means that all unit cells move in the same direction. So let me go back maybe at explaining it where I had the sketch for it. So let's go back here. I think that was it. So if we look at gamma, the phase factor in here, Q means gamma is Q equals 0. So this means 1. What does it mean? This phase factor describes how different unit cells relate to each other. And since this is 1, gamma means all unit cells have to move in the same direction. So if we solve this problem, then we get acoustic modes. So we get one solution in which all atoms in the unit cell move in the same direction. And then, since gamma tells us that all others have to move in the same direction as well, everything moves in the same direction. Okay? Is that clear, Nihat?
Yes, till now it's very clear.
And so the whole crystal moves. And this, if the whole crystal moves, you cannot gain or lose energy. That is why the frequency here is 0. And conversely, if you look at the optical mode, you get a different solution for the unit cell, because here one atom moves to the right and one to the left. Still, since we are at gamma, the periodic images move the same. So all black atoms in the crystal move in the same direction. And all red atoms in the crystal move in the same direction. But since we have basically these atoms moving against each other within the unit cell, we get some finite energy for it. Okay? This is what happens at gamma. Is this clear for everybody? If not, feel free to ask and also interrupt Nihat.
Yes, it is clear. But I just want to ask a question. We have 3 branches in acoustic, and we have 3 in optical. They are all the same? They have the same value?
No.
Yeah.
No. So here in this one-dimensional problem, we have just 1 and 1. In real problems, in real systems, let me go back. Where did we have that as a summary? You always have 3 acoustic modes, regardless how many atoms you have. Why? Because these 3 acoustic modes really describe just the lattice vectors, how individual unit cells behave with respect to each other. So you always have 3 acoustic modes. And then you have 3n minus 3 optical modes.
Okay, in case of silicon, they are 3 multiplied by 2 minus 3, right? It's 3.
It's 3 again.
Okay.
And then if we go back to silicon, you have to really look at the crystal symmetry. So let's do it here for the we have one where it's, I think, more clear. Yes, this for instance. So I mean, if then there are always 3 present, but it can be that in high symmetry crystals like silicon, some of them are degenerate. Okay? So for instance, if you look at the acoustic modes, here in silicon, you see the 3 acoustic modes you only see along this path from gamma to K. There you clearly see that you have 3 acoustic modes.
Yes, yes, you are right.
But here from X to gamma, you see that 2 of them then are degenerate. And you only see, in principle, in this plot, you only see 2. If you really do the calculation, you would see that you get this thing twice.
Yes, 2 of them have the same value or something like this.
Exactly. 2 of the same have the same value. And the same is for the optical modes. You see very nicely. Here you have these 3 optical modes present along this quite complex path from gamma to K. But then again, for instance, here in X, 2 of them get the same value. This is obviously something that you only get in very high symmetry crystals. If you look at the more complex systems, here at zirconia, you essentially see that almost in all cases you can see the optical modes not being degenerate. And it's only in some very, very high symmetry, again, you see that this that they get the same values. As most of the time you see all of the modes present.
Yes, I get the point.
This is happening really just when plotting. If you do the calculation, you always get all values.
Yes.
And then this is also, for instance, let's say helpful, for instance, when we looked at this density of states, because in the density of states, then you typically see, you really count all of them. And so you get a little bigger peak here where you have 2 acoustic modes than here, where you have just 1 acoustic mode. And there you really see that there are 2 presents, even in the plot.
Thank you a lot.
Good. Do we have some more questions?
Actually, in the chat, we have another 2 questions. One by Abu Sandal. Why can standard DFT calculations not predict temperature effects directly?
Why can it not predict temperature effects? Okay. Then let's go back to the very beginning. So what we actually do when you do your standard DFT calculation, you take a lattice, you give it a certain kind of position, you calculate the energy with your DFT code that you like, and you get the energy and forces. But you get the energy and force for exactly this position. You don't get any more information. You don't get any information about how the atoms move. If you want to know how the atoms move, you have to go beyond standard density functional theory. Maybe something that I should have specified, if you can, for instance, what you can do in electronic structure theory is get the temperature information for the electrons. That you can include. That is something that is, for instance, important in metals, but is a relatively minor contribution to the total free energy. So I've not discussed that too much. But so to make it very, very simple, when you're doing density functional theory, you solve the electronic problem for fixed nuclei. If you think about the first lectures where you applied the Born-Oppenheimer approximation and so on, what you said, the atomic positions are just a parameter that defines my Hamiltonian. So you only get a solution as a function of that. If you want to look at free energies, at thermodynamics, in which you account for the motion of the nuclei, you have to start moving that. And that is not included in the electronic Hamiltonian. You really have to solve the nuclear Hamiltonian on top of that. And to solve the nuclear Hamiltonian, you need to have the information about the actual energies, and that you get from density functional theory. I hope that was a little bit clearer now.
Sorry. There is also another question by Fatima. She's asking, how does the collision between... Okay, Abu Samdal, he said, okay, the answer is clear. For Fatima, how does the collision between molecules affect the energy?
How does this affect the energy? So collision is a very hard thing. So look a little. Maybe I think if you look a little bit at this movie, and I think I made this movie is at least at 2000 K. This is again this zirconia 2000 K. If you look a little bit closely, you see that the atoms really never collide. It's not that they smash into each other. You would need a lot more energy to get these atoms closer together to really speak about collisions. What you see here is that you really have atoms, they don't like to get close to each other. So you need a lot of energy to push them together. And in a standard material, what you see is that they're actually only vibrating, moving a little bit around the equilibrium positions. And this is exactly why we can do a harmonic approximation. So if we go back to this kind of simple sketch of a harmonic approximation that we would have here, so where we described basically our potential energy surface as a function with such a harmonic parabola. So this is the kind of regions where atoms typically move. Okay? So you're close to equilibrium, and maybe if you go to higher temperature, you're no longer that close to equilibrium and the parabola doesn't work that well. But a real collision would happen up here. And this is typically in an energy range where the crystal would have long melted. I hope this was a little bit clearer.
Fatima? Okay, if there is no other questions, we can continue.
So let me show a little bit.
Okay, it's quite clear.
Good. Then I would give you just a little bit of an outlook. Also an idea how you can go also beyond harmonic approximation and to account for non-harmonicity, what one really has to do and what is necessary for doing that. Also to give a little bit of an idea where current research is going. So as I've told you before, actually everything that is not captured by the harmonic approximation we typically call anharmonic effects. But what does this really mean? If we look at actual potential energy surfaces, one would say, yeah, this looks actually quite good. Here the harmonic approximation should hold very well. If the orange is a real potential energy surface, the blue one is a harmonic one, they're very close. You can have situations a little bit like that where we would say, okay, I'm not totally convinced. Maybe at low temperatures, the harmonic approximation is quite good when we're close to equilibrium. But if I go to higher temperatures, no, maybe not so nice. You can have situations like here, where also you would say, at low temperature, the harmonic approximation will for sure hold. But if I have high enough temperature to come in this other minimum and I will stick around here, the harmonic approximation will not hold. And this is even worse if we have so-called imaginary frequencies like we had in this zirconia example. Then obviously the atoms will mostly stick around here, and this harmonic approximation with this parabola pointing downwards here, this is not really meaningful. And if we look at this in this very simple one-dimensional picture, this becomes relatively intuitive, but can we find ways to also give them a more quantitative, really a number insight to discuss this more clearly for real materials and not just in this kind of sketches? And for that, a couple of years ago, together with a PhD student of mine, we tried to answer these questions. How can we compare anharmonic effects in different materials? And then we followed a very, very simple scheme that is also easy to follow. Here, you first run your molecular dynamics to simulation, and you try to explore your potential energy surface. So you have your potential energy surface here, you run your molecular dynamics, and what you then do, you actually store the energies that are calculated in this molecular dynamics run, and you look at it at different positions, and this you store. And then in a second step, you say, good, now I have these positions. What would the harmonic approximation actually predict at these positions? And since you run one Phonon calculation at equilibrium, this gives you exactly this parabola, and then you can easily analytically calculate what the energy at these different positions is. Now, you already see here that you will have some points in which you have quite a nice agreement, and there are others in which the agreement is not so nice. And what we then do, we look at this actual difference and do an average over this position, so over this trajectory, to look at how harmonic and anharmonic potential energy surface compare. In practice, we then do not use the energies to do that, but we use the actual forces. Because for each calculation, we get a lot more forces and values for forces than for the individual atoms. And this has also the advantage that we then can get some insight onto the individual atoms. To give you an example, we have done that for silicon. Silicon, again at 300K, and what you see here is basically the forces that we see in a DFT molecular dynamic runs compared to what the harmonic energy would predict. And if you look at this correlation plot, it actually looks quite nice. So you see that essentially, largely, harmonic potential and DFT agree quite nicely. And so this is a very well behaved harmonic material. This is what you also know and would expect from something like silicon. On the other hand, we did the exact same calculation, but for something different. This is copper iodide. It's also a zinc blended structure, so a relatively simple structure. It's also run at 300K, and you immediately see that the distribution and the correlation that we observe between DFT and harmonic calculations is quite different. So on the one hand, this distribution is quite broader. And if you look closely, here you see some points, for instance, where DFT calculation point in one direction and harmonic forces point in the complete other direction. So what is going on here? So here, what it turns out, if you look at the system more closely, we have really a system that looks like that. Here, the harmonicity is very dominant. And if you look at the dynamics a little bit more closely, you will discover that actually this point corresponds to a point in the dynamics where the system has explored a different minima. And this down here, for instance. And so the DFT calculation point in forces point in one direction, while the harmonic forces in the complete auto direction. So this is such a system like here. So this gives you, again, a qualitative idea of what goes on, but what you can then do is also define a metric. We call it the non-harmonicity metric, and this is nothing else than the standard deviation of this distribution. If you calculate the standard deviation, you get a value of 0.15 now, here, for silicon. You can then, if you go to all the derivation, you can then analyze this, and you will discover that this tells you that 15% of the forces come from anharmonic effects, while 85% come from harmonic effects. This is obviously tells you, good, this is a nicely harmonic material. Copper iodide, on the other hand, has a much larger standard deviation, so you get a value of 0.5. This tells you that on thermodynamic average, 50% of the interaction come from anharmonic effects, while 50% come from harmonic effects. So this is a very anharmonic material in which anharmonic effects and harmonic ones contribute equally. So this is the kind of information you get out of that. And what you can then do is really start looking at different materials, at different systems, at different kind of techniques. So here we have taken, for instance, a material test set with 200 and plus materials. They are all relatively simple. There are 100 rock salts, 70 zinc blender, around 50 wurtzites, plus 10 perovskites. And then we looked on how this anharmonicity changes across material space and across temperature. So what you see, for instance, here at room temperature at 300 K, is that you see many materials, almost all of them, a huge majority, is very nicely harmonic and as harmonic as silicon. So in that regime, the harmonic approximation works very nice. But even there, look, at 300K, there are some materials that start getting quite anharmonic. So even in that regime, you sometimes have to be careful. So it's useful to look at into that kind of things. What happens if we go to higher temperatures? Here to 500K and then to 700K. The number of atoms that behave perfectly harmonic become much, much smaller. So here at 700K, almost none of the materials are in this regime, and very few are harmonic. On the other hand, the materials that have strong influence of anharmonic effects become much more prominent. So this is not too surprising. We've discussed from the beginning that the harmonic approximation is a low temperature approximation for small displacements. So it's not too surprising that anharmonicity increases with temperature. What you already learned here, however, is in which materials this happens when. You then can even go looking into how different materials behave. And this is, for instance, one of these more complex materials. This is a perovskite, cesium lead iodide. Here you see quite clearly that this system has a very quite broadness, and then also you can see that cesium is really the one doing worse. So cesium is the one where you have almost no correlation anymore between DFT and harmonic forces at all. And this gives you some insights on this kind of effects. And to give you a little bit of an idea how these anharmonic effects then affect our kind of systems, give you one example, one possible technique to include that. What you can do is to explicitly then start evaluating not just the harmonic part of the Taylor expansion, but traditionally include third order effects, so the next order in the Taylor expansion. And what then happens is that you no longer get a nice band structure, but you get a so-called spectral functions. So these phonon band structures are no longer sharp, but they get a finite width. And if you compare that for this kind of system, you notice two effects. On the one hand, you see if you put them really side by side, you see that actually the frequency changes slightly. So what you see, at higher temperature, anharmonicity can reduce your phonon frequency. So you see that slightly here and slightly here. And on top of that, what you see is that you get a finite line width. What this means is that your phonons get a finite lifetime. They only survive for a certain time, and with that, the shorter the lifetime is, the broader this distribution becomes. And this is something that you can get out of anharmonic effects with this kind of theories. And lastly, I would like to discuss some additional anharmonic effect that is quite interesting, as we discussed before. What you can do is you can look also at the harmonic energies and at the anharmonic effects for lattice expansion. In the harmonic approximation, if you just would look at one lattice constant, you would have no lattice expansion at all. What you really need to do is to start mapping out your free energy for different lattice constants. And if you do that, you can then calculate the lattice expansion coefficient, which is nothing else. How does your lattice expansion change as a function of temperature? And here, we've done that for silicon here, and you see a very nice example. It's a very famous example that holds for many group 4 and 3,5 semiconductors. Interestingly, at low temperatures, you have a negative lattice expansion. So you heat the system up and the crystal shrinks instead of expanding. And you can look at it by looking at the phonon band structures that you can actually calculate. And what you see is that in silicon, if you expand your volume, the optical frequencies decrease in frequency. This is expected because you give your atoms more room to move, you have they interact less strongly, and so this is what counts at high temperatures. And so in that case, your free energy decreases for larger volumes, and this is what gives you the expansion at very, very high temperatures or at room temperatures. At very low temperatures, however, only the acoustic modes are occupied, and only those give you a contribution. And in that case, the frequencies increase with larger volume. So here the crystal has the tendency to shrink if only these acoustic modes contribute. And the reason why this happens is that silicon has a very specific tetragonal sp3 kind of electronic configuration where they really want to stick around that part. And so if you move them out of that very nice coordination effect, the energy increases and the crystal does not like that. And that is something that is an anharmonic effect that you can also count in the so-called anharmonic quasi-harmonic calculations to account for this lattice expansion. Good. So with that, I would come to the end of my lecture and would like to discuss a little bit more. Let me just go a little bit back, thank the people in institutions where I've worked with. So many of this zirconia example that I've shown you that go back 10 years. I've done that as my postdoc at the University of California, Santa Barbara with Chris Van der Walle, Carlos Lewis, and then here at my time in Berlin with Matthias and now with Carsten, with the more newer results. So I have to thank them for supporting my group over the last years. And with that, I would get back to my take-home messages. And first, thank you for your attention. I hope I could teach you a little bit and give you a little bit of an insight in this exciting and complex topic of actually doing phonon calculations. I hope you will get even more insights with the workshop this afternoon when you really do these things. But if some additional questions arise, either ask me now or write me an email. I will be reachable. I can try to answer them if there's some more open questions, and then we can even talk next week if you would like to. So thank you very much for your attention.
Thank you very much, Dr. Christian. It was a very interesting and enjoyable lecture. Thank you so much. Now for the participant, if you have a question, you can just open your mic and ask. You can also write your question in the chat. Okay, if there is no questions, we conclude. Thank you so much. It was a pleasure to have you today.
Thank you very much. And as said, if some more questions arise, either afterwards when looking at the slides or during the tutorial or anything, feel free to write me an email. I would be happy to discuss more things with you.
Okay, thank you so much.
Thank you very much. And